All right, so I'm gonna get the lecture started. Are there any questions related to the homework assignment? I think this is the last chance that you can ask questions in class, and if you want to go to the lab and ask questions in lab, that's cool too. But are there any questions with that homework assignment, with the Fibonacci homework assignment? Okay, no questions. I'm really surprised. Okay, there has to be some kind of questions.
It's not working right.
Okay, if it's not working right, okay, that's not a question.
Yeah, I know, that's why.
We have to do it
It's a question.
turn it into a question. This is Jeopardy, right? We have to do it the Jeopardy style. Yep. Yep.
So I did have a question. I'm kind of stuck on the calling two recursive functions within one function. So like you have the return one and return two.
Okay.
Yeah.
So let's take a look at the algorithm first in C, and then we'll try to figure out, what we need to do in assembly. Okay. I'm going to close that. It's a little bit distracting. Okay, so we want to look at the C code first. So int Fibonacci, taking in n as a parameter. And the first thing you want to do is to say, now there are several ways to do it. You can check the range instead of just checking whether it's 1 or 2. You can check the range, but checking the range is not going to save you a whole lot of time. So I would just check individually. If n is 1, and if you don't want to have to use a local variable to store that, you can kind of do this. Okay, I'm not going to oppose. I won't oppose any code that does that. Now the interesting thing is if this is what you do, you don't need an else. I'm not saying this is a good approach, I'm just saying that you don't need an else. Oops. There we go. Okay, so this is one representation of Fibonacci in C code. Okay. So the question now is, okay, first question is, why don't we need the else? Isn't that going to mess up the logic? Well, why do you need an else in a conditional statement? What does it do? It's an alternative, right? So if you're not going, so the else makes sure that if you take the then branch, it won't also do the else branch. Is that making any sense? In this case, if you take the then branch, which is on line 5, do you have a chance to continue execution in this subroutine? No. Same thing with line 9. Okay, if you take the then branch, there's no way you can continue the execution of this conditional statement. So that's why when you put a return like this inside the conditional statement, you don't really need the else anymore. Okay, because the behavior of this program is going to be exactly the same as the one with the else, which is doing it properly. Okay? Now, do I encourage people to do it without the else, even though it is going to be exactly the same in terms of behavior? No. Because this is a simple program, simple enough where there's not a whole lot of probability that I want to come back and add some more code later on. Okay? It's that coming back and add code later on that is the problem. Okay? Because a lot of the shortcuts where but it works, right, would be okay with a small, simple program or simple subroutine. It is clear what you're doing. You're not going to have a problem without the else, like in this case. But when you come back and say, but I want to add something else to this particular code, there's something else I want to do with the else case, then it becomes a problem. Okay, this is not a C programming class. I'm not going to go too deeply into that discussion. So, are there any questions about this particular implementation of Fibonacci, which may not look the same as what we had before, but it's close? Is that okay? All right. Do we know how to get back to n? That is the first question, because n is a parameter. You have to be able to get back to the parameter before you can do anything else. You have to be able to compare the parameter to 1 and then to 2, and then use it inside the parameter as you perform recursive calls. So the first question is, do we know how to get back to parameter n? Okay, where do we find it?
stack.
On the stack, very good. It is also the location that is right after the return address. Now, when they say after, it's higher, okay? Because when you push things on the stack, the first thing that you push has a higher address, and then the next thing you push has a lower address. Okay, so that is good. Do we have a question of, once I know the value of n, how do I compare that to 1? Are there any questions about that part? No, we have the compare instruction, and then we have the conditional branch instructions. So in this case, this may not be the easiest way to implement it, but I'm pretty sure most of you can figure out how to use the existing instructions to figure out, oh, okay, if it is 1, this is what I want to do. If it is 2, that's what I want to do. If it's neither, that is what we want to do in the recursion. Okay? Does everybody know how to do this part? Okay. Yep.
Yeah, I had a question regarding recursion. So I guess I'm just confused when you continue down the stack per call for each function. I'm just confused when you get to the bottom how it goes back up.
It's the return sequence that goes back up.
So it's like you assume that these values will be here, and you just keep jumping back up.
Okay, so instead of doing this, which is your homework assignment, let's do another one. Okay, so let's do another one like this. So I wanted to do this one as a sum. Okay, and it is going to compute 1 plus 0 plus 1 all the way up to n. That's what it's supposed to do. Is that okay? So I'm just going to comment here and say return 0 plus 1 plus 2 all the way up to n. But I want to do it recursively. So just like last time, the question is, how do we implement this in a recursive way? And the answer is, we think of the easy ones first. Okay? In which case do I not have anything to do? That is the question.
N equals 0.
Okay, if n equals to 0, I have nothing to do because I just return 0, right? Cool. What do we do in the other case? Now I'm using this style of programming, putting a return in the middle. This way I don't need to use a local variable result, okay, which is complicating the assembly code a little bit. So I'm using this special case so that we don't have to deal with that. Okay, so what if n does not equal to 0? If I tell you ahead of time that I won't try to trick you and n is always non-negative, what does that mean when I get to the else branch? N is at least 1, very good. So I can say, oh, what about this? Return n itself and then plus, sum of n minus 1. Would that work? Okay, that's okay. It seems to me that this is reasonable. Okay. So now the question is, how do we implement this in assembly using our toy processor? Okay. Are there any questions about the C version of this code first? Okay. So if there are no questions about this, then I'll open up another mousepad on the side to work on the assembly code for this one. Oops, that's not. Mousepad, there we go. Okay. So we have sum as a label because we need an entry point to get into the subroutine. Now I always kind of like to comment at this point and so that I know what is on the stack. So I know what is on the stack is going to be n, which is a integer. We also know that with return address is also on the stack, and in this particular order. N has a higher address, return address has a lower address. They're right next to each other. Where exactly are they on the stack? I don't know for sure, but I do know this. I know D is pointing to the return address at this point. Is that okay? Now, it's just my habit, to kind of put this at the beginning of a subroutine, just so that I am aware of, where is everything at the entry point of a subroutine. Now, you don't need to do this if you think that I can remember all that stuff. That's cool, not a problem. Okay. All right, so the first thing we need to do is to find n, okay? N is almost where D is pointing to is almost n, but not quite. So the first thing we need to do is to go, okay, let's go find n first so that we can compare. So the first thing you need to do is to make a copy of D, because we don't want to mess around with D, okay? Every time you want to do some calculations with D is when you need to allocate something on the stack or deallocate something on the stack. Otherwise, don't touch D. So what you want to do is to copy D to some other register. So this is where it is kind of important to remember the ordering, because I messed up the ordering, remember, in like a week ago, okay, and it took me a little bit of time to find out, so that is why the program is not working. So it might be helpful to indicate what it does. A is going to be a copy of D and not the other way around, okay. So now that we have a copy of the stack pointer, we can now manipulate the copy so that we leave the stack pointer itself alone. So we just say, oh, how about just adding 1 to A? As a result of this, A is now D plus 1. Does that make any sense? Yep.
So when you're talking about the return address, are you talking about the return address of the previous function that was called?
It is where you're supposed to go back to when this subroutine is done.
So it's the previous function that's called it.
Whichever the function is. Where it's basically, when the subroutine is done, it needs to find out, okay, but where am I supposed to go to continue execution? That is what the return address is telling you. Where do you go to continue execution? Okay. All right, so now the next thing we need to do is to go, oh, so A is already pointing to n, which means A is the address of n. So it doesn't hurt to say that A is actually the address of n at this point. It is both. It is both D plus 1, whatever is in D plus 1, but it is also the address of parameter n. Am I comparing the address of n to 0? No, I'm comparing the content or the actual value of n, which means I need to dereference it once. So LD would do it, LD A from indirect A. So this basically is saying A equals to star A, dereference A, which is also just n. So A would become n at this point. Are there any questions at this point? Because if you have any questions, this would be a good time to ask. This is all good so far? Yep, go ahead.
So why did you dereference A again? The last one? I just missed that.
This is the first time I dereference. Because at this point, A is D plus 1, which means A is pointing to the byte on the stack that contains the parameter n. Okay? So I'm not going to compare the address of n to 0. I'm comparing the value of n to 0. So given the address and you want the value, you just need to do a dereference.
Okay, thank you.
All right, so now that we have n, or A, register A, is actually parameter n, we can do the compare. And comparing to 0 is kind of special because you can use AND AA to do it, or or AA, depending on which one we hijacked. I think we hijacked OR, leaving AND available. So AND AA would do the trick. It's the same thing as comparing A to 0, but without having to use up another register, put a 0 into it first, and stuff like that. So this is the same thing as compare A to 0. And what do you think is going to happen here? What do I need to do after this?
Sure.
Well, I need to do a conditional branch, right? I need to look at the result of comparing A to 0 and then go like, well, which way should I go? And which flag may be useful here? JZ is going to be helpful. So we say JZI to return 0. Now you can use return 0 as a label name, which is really good because it is self-explanatory. So that means at this point we will have a recursive, this is the recursive part, and the return 0, for the label here, it just has to return a value of 0. Okay. So I like to write code like this. In other words, every single time I encounter a conditional branch, I would indicate what does it mean if I do not take the conditional branch, and then I immediately make the label and also comment what does it mean if I get here at the label. Yep.
So I think Alex mentioned this the other class, but conceptually it seems like you start with
You can do it in both directions. The
But the way
advantage
you
of
do it,
starting,
yeah.
the way I do it is from the inside out, but when you do it inside out, the best part is you can debug it, bottom up as well. And that's a better way to do debugging because you make sure that whatever you rely on is working 100% before you build any code upon it. So that's partially why I personally like bottom up coding. Even though when I analyze the code, I'm gonna do a top-down analysis to break it down to small pieces. But when I actually write the code, I would do a bottom up.
So is that how you do it, even if the project becomes like much larger?
Yeah. Yeah. Yep. So it's a bi-directional approach. When you analyze and you try to figure out what pieces do I need, it's a top-down process. But when I'm actually coding and debugging and verifying the code is working, it's a bottom-up approach. All right. So now we also need one more thing. This needs it needs an unconditional branch here in order to get to the end of sum. So we'll just say end of sum, because otherwise it will just kind of go through the return 0 code as well, which is not good. I don't want it to fall through like that. So I need end of sum here, and I would just say return to caller to remind myself what does it mean if I get here. Okay. All right. So we'll do the recursive call. Well, we'll do the easy one first. Returning a 0. That's an easy one. You can do it in several ways. You can do LDI A0, which is the most intuitive way to do it. But if you want to save a byte and also save a little bit of execution time, the other way to do this is a sub AA. Subtracting A from A is going to guarantee that A ends up with a value of 0. And nobody really cares about the flags register after this anyway, so it's okay to mess around with the flags register. So that's one way to do it. All right, so now we get back to the recursive part. The recursive part is this part here. I don't really need to deal with this n plus at this point, because until I know what the sum is returning, I don't really need to know what is n plus. Question, go ahead.
When we return 0, don't we return to caller as well? Don't we end the subroutine
Yeah, but
return
that's why
caller?
we have an unconditional branch or falling through to end of sum here. I'll deal with that later. Yep. So at this point, you can see that when I write code, it's not linear. I usually do not write code in a linear fashion because I just take care of the branch, the structure of the branch first, and then I go back in and just add the code to do what the branch is supposed to do. All right, so the recursive part has to do all of this stuff here. So I'm going to deal with, okay, let's compute n minus 1 first. Okay. I can go through this logic here, okay, everything from here all the way down to here. I can repeat this code in order to get to n. Or I can just look at this code and go like, hey, register A still has the value of parameter n at this point. Right? Because nothing has changed after this point, and AA does not change A. So we can still use A as register A still has the value of parameter n. So depending on how much I want to optimize this code, this is what I'll do. Okay, in order so that I don't have to recompute what is n, I'm going to do something like this. So I'm going to push n on stack first. In other words, I'm going to save the value on stack first because I'll need it back later on. Okay. So to do that, you have to first decrement the stack order, allocate byte on stack, and then do a st indirectly with a. Okay, store n on stack. Okay, so now that A is stored on stack, I can just mess around with it, in order to call the subroutine. There's another way to do this too. You can also store n minus 1 on the stack, and then later on you retrieve it and add 1 back to it. That becomes n again. So there are several ways to kind of optimize the code. This will use 1 more byte on the stack, which is okay, So if you really want to optimize how you use the stack, you can do 1 more decrement on A first. So A is n minus 1 at this point. So you store n minus 1 on stack, which becomes the parameter of the recursive call to sum. Is that okay so far? So parameter n is now pushed on stack. So parameter n, let me be more clear, of the recursive call is now pushed on the stack. Is that okay? All right. So once we have the parameter push, it is just a matter of calling the subroutine. Now when you're calling a subroutine, it doesn't really matter whether you're calling the subroutine that you're in already at this point, which is recursive, or you're calling some other subroutine that is not related. It's still the same mechanism. So the first thing you have to do is to find out, okay, when the subroutine is done, where is it supposed to go back to? And I just use some underscore red return to be the label. So the first thing you need to do is, well, you can decrement the stack pointer first. Okay, so we allocate byte on stack for the return address. And then you have to do a LDI, use a particular register. At this point, I can use A again because A is already saved on stack. It is already pushed on the stack as a parameter. So I can reuse A at this point. It has no particular meaning at this point. And then you do a store. So this way, the return address is stored on the stack already at this point. And then you can just go ahead and do use a jump I to go to the beginning of the subroutine that you're calling, which turns out to be the subroutine that I'm in at this point. But it really doesn't matter whether it's the same subroutine or not. Yep.
So the return address is, this is a different one now because it's sub-return.
What was the question?
I'm just trying to clarify because like in the
Okay.
beginning when you first call the function sum, it's the return address of the main function. It's the main return.
It would continue execution somewhere in main.
Yeah.
But I don't even have main written yet.
I know, but in this case the new return address would be sum return.
Correct. It's whatever is after, it's the address of whatever instruction is after the jump I instruction that will get you into the subroutine. Because it has to come back at some point, right? When you're calling a subroutine, it has to come back at some point. So you have to tell the subroutine where it's supposed to come back to, and that's why we need to label sum underscore RET. Yep.
Shouldn't the sum return address in the parentheses be sum right? In this case?
Say that one more time.
The return address in parentheses be sum right?
The return address is sum right.
If you comment for
On the
like
comment block?
for 17, line 17,
On line 17.
we're decrementing for the sum return
Right.
address,
I think he said
I'm just using return address as a general term.
Oh,
Yeah.
But it is for some reason.
But in this case specifically, it is sum right. It's the label of the return address. Yep.
So if we were doing this twice, we were calling two sub functions. How would that look?
That you have to look at 5712, which is a program that we did last week. So 5712 is an example where you have two function calls, and then you have to add the return values of both of those invocations to become your own return value.
Well, I was looking at that. What confused me was it was like so when you're in main, you call 5 or something, right?
When I'm in main, I call 12.
Okay.
12 in return calls 5 and it calls 7, but then you have to add the return values of those two particular invocations to become the actual return value of 12.
So I mean, in that case, then you would just call, vid n-2 and then vid n-1.
Every time you call, it's going through the same thing. When you're calling, there are exactly 3 main phases of calling a subroutine, and any way you want to call a subroutine, you have to go through these 3. Some of these are optional. The first one is to push all the parameters on the stack. Second one is to actually do the call, which means you have to allocate the space for the return address, put the return address on the stack, and then do an unconditional branch to the subroutine. That's the second phase. And hopefully the subroutine will come back to you at the label that you designate as the return address, as the return point. So at that point, you have to deallocate the parameters that you push on the stack, because once the subroutine returns, those parameters have no use on the stack anymore. Okay, so every time you call a subroutine, you have to go through those three phases. So if you have two subroutine calls within the same expression connected with a sum or plus, you still have to you still have to call the two subroutines as the way I described. The trick is the return value of the first invocation would have lost if you do not save register A on the stack first.
Yeah, because you said that in the previous video.
Right.
What I was just confused about, I just thought it was weird how the two separate functions were dependent on each other. It was you had to do 5 first and then 7, and then it would go back to the 12 function. So in the case, I was just how's that? Because in the case of recursion, then you're I'm just having trouble visualizing you're so far down the stack, and then it just goes back and forth all the way up to.
This is one of those cases where looking at the pine needle is better than looking at the forest.
Okay.
Because the mechanism of returning does not really matter whether you're recursive in a recursive situation or not. So it makes no difference whether you're in the subroutine 12 and you have to handle the return value of 5 and then handle the return value of 7, or whether you're in a Fibonacci situation where you have to handle the return value of fib of n minus 1 versus fib of n minus 2. Those two scenarios are exactly the same, except one has parameters, the other one does not. But the way you handle it will still be the same. It doesn't matter whether it's recursive or not. Makes no difference as far as the mechanism itself is concerned.
I guess it just seems like if you added additional variables to add, it seems kind of tedious for it to be all interdependent like that,
You mean the use of n minus 1 as one parameter, n minus 2 as another parameter?
No, just separate invocations. They're all dependent on each other in terms of
Okay, I would address that question after we are done with this one. Yep.
Okay. Can we, instead of jumping to sum return, jump to just end of sum straight away?
Say that one more time. Instead of this one,
line 18.
line 18.
You're adding extra sort of variable sum return, and then the point of sum return is just to jump to end of sum, but we already have end of sum down below. Why don't we just jump to end of sum?
But we're not done yet. We're not done yet. We are not gonna. There's more code to write here.
Oh, okay. Sorry.
We are only done with phase 1 and phase 2 of this particular call. Remember, phase 1 is to set up the parameters. Phase 2 is to call the subroutine. Phase 3 is to clean up the parameters. We haven't even cleaned up the parameters, right? So you need an increment D to clean up, the parameters. In other words, you're deallocating the stack space used up by the parameters for this invocation of sum. And then we got several things to do because we are just done with this part in C code. We still have a few things to do, right? We still have to figure out, but we are supposed to add n to it. So how do we do that? Well, maybe we shouldn't do this yet. Because D is pointing to what? At this point, D points to somewhere on the stack, which has the value of n plus 1. I mean n minus 1, right? And what do we need?
We need to increment.
We need n, right? So we need to increment it. So the best way to do this is to get it first, and then you increment it. In other words, you're popping it, okay? You're retrieving what you have stored previously on the stack into a register. So that will be done with an LD instruction. So I'm going to put it into, say, register B, which is not used at this point. I do not want to use register A, because register A has the return value of the call to sum at this point. I don't want to mess around with A, but I can use B. Okay, so B is n minus 1 at this point. Then we can go ahead and clean up the parameter, because now we have used it. It's good, it's in B. So it's time to increment B. So now after this instruction, B is going to be the same as n. We know A is the return value of calling sum with n minus 1. So now we can just add those two. And we'll use A as the destination register, because it is supposed to be the return value register to begin with. So now A is going to be sum n minus 1 plus n, which is what we want. And then you can go to n of sum, which is down here. Now we can say, okay, now that the stack is balanced, we can go ahead and assume D should point to the return address at this point. So that makes it easier to specify the return code. So I just have to do an LD to retrieve the return address into a register. I cannot use register A at this point because A already contains the proper return value. So I have to use either B or C. I'm going to use B. Okay. B as the return address at this point. Then I have to increment D. D allocate return address on stack because it is now utilized. It doesn't need to be on the stack anymore. And then we do a branch or jump based on register B. So we can now continue execution in the subroutine that called me. Is that okay? All right. Is that okay? Yep.
Okay, so you're continuing. Can you go back up and like go to the return or sum return?
You mean here?
Yeah.
Go ahead.
So does that mean you're jumping to sum return?
It is jumping to sum, but remembering that when sum is done, it has to go to sum return.
So I'm talking about at the bottom. It says jump to return address. I'm asking you which return address.
It depends on who called me.
So if sum called it, would it
If sum called me, then I will be going back to sum underscore return that particular label.
So then you'd be like adding them all up. If
No, I'm winding at this point. This is unwinding because every time you see that you are incrementing the stack pointer, you're unwinding something on the stack. You're deallocating something on the stack. Is that okay?
Yeah.
All right. Any other questions? Yep.
For like absolute clarity, is it possible to make like a flow chart of this version? Because like this flow chart will be super easy. Yeah, there's just one branching. You go here, you go here. But for that, it seems like there are so many extra points where you have to visit before it's going to be executed.
Well, the flowchart only in this case would only have one single branch, right? It only has one single branch because there's only one compare up here. There's only one conditional branch. In other words, this flowchart will be super easy to draw because it only has one diamond where it has two outgoing edges. Because that's the only conditional thing that we can do in assembly is j blah 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 I, where the blah 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 is a flag. Yep. Okay. So go ahead first, and then go back to you.
Okay. So I mean, you said unwinding,
Mm-hmm.
but if it's unwinding the sum return, that means it's just taking all the previous return values and processing them back up and unwinding, right? Like returning all of them.
How about this? I would trace this code, so that you can actually see what would happen to the stack, what happened to the registers as we execute this program line by line. Okay? But I can only do it with like a really not a whole lot of number because otherwise it would be really long. Okay. Okay. So let me finish the entire program first. Assemble it, put it into the simulator, run it, make sure it works, and then we'll go ahead and run it in, trace it manually. So now we just do a sub dd, okay, initialize stack pointer, which is typically not really needed because all registers start with a value of 0 as you reset the processor. But I'm going to do it anyway just to make sure everything is initialized correctly. And I also know that in main I want a halt instruction because I don't want it to execute past this point. So the rest is the actual main subroutine. So let's just say that I'm interested in doing the computation and just leave it in register A. I'm not going to do anything with it. I'm not going to store it anywhere. Just put it in register A. So How many times do we want to go through this recursion? If I use a 0 as a parameter, it won't do any recursion. If I use 1, it will do a recursion once. If I use 2, it will do the recursion twice. 2, okay, 2 is good. Okay, so we'll load A with 2, decrement the stack pointer to allocate the space, stda in order to push the value of 2 on the stack, which is our parameter. We have main return as a label to get back to. So now we have to do LDIA main return, decrement the stack pointer again, store where the stack pointer points to, A, which is our return address. And when we get back here, I'm going to do the nice thing and actually do the deallocation of the parameter. Even though there's nothing to do after this point, this is the right thing to do, is to balance the stack. Okay, so by the time I get to 11, A should be 0 plus 1 plus 2, which is 3. Is that okay? All right. So we'll do a Control-C, go back to my browser, and look for that folder. There we go. Assemble. And we'll just a delete, but don't mess around with B, okay? Because B actually contains the error messages. Yep.
Did you ever jump to the subroutine?
Jump to a subroutine? Oh, I forgot that. Okay, good point. Okay, because I set up the point, I set up the stack, so it's ready, but I forgot the actual jump. Good point. Thank you. Okay, that's important. Okay, so paste. We got everything here. We look at the messages. Somebody said, I think I encountered the same problem too. You can only see the errors in this particular tab. Okay, so nothing here either. So as long as the RAM file tells you that this is a raw, instead of there are errors, it should be safe. So we go ahead and save, download as CSV, and we'll put it into the temp folder, call it sum. Now we have to start up the virtual machine, the simulator. And go to processor as our subfolder, processor with DPC2. Alright, click the reset button and load the program on temp sum.csv. There we go. And if we are relatively confident this is going to work, we can just kind of let it rip and check register A. If not, it is a good idea to log certain registers and certain memory locations. So I'm going to log several things. I'm going to log the program counter. Logging the program counter is helpful because at least it will tell you, what instructions have you executed. Okay. Yep. I don't think so because when we ran it last time, it got the right wrong already. It should still be there. So program counter is good to log. Within the register bank, you can log all 4 registers if you want to. I know for sure register A is important because it stores the return value. And the register D is also important because it's the stack pointer. The other 2 registers, depending on how comfortable you are with the program, you may not need to log those. And then we have to go to RAM and log the last few locations. Because we know for sure that this is going to be used as the parameter. This is going to be used as the return address. This is going to be used as the saved this is going to be used as a parameter in the recursive call, and this is going to be used as a return address, parameter, return address, and I think that's all we need because we should only have 3 levels of recursive call. But I'm going to log a few more locations just to be sure, okay? Because we really should not be getting to those particular locations. Okay, so we have everything set up. Let's go ahead and let it rip. Okay, it's done. Let's go ahead and stop this. And the first thing we check is register A to make sure that register A has the right value. Since the log has register A already, we can just check that. So let me make this bigger so we can see all the columns. All right, so when you look at these, register A is this one, the second column. So when you look at the second column, it ends up with a value of 3. That's good. That's what it is supposed to be. And then when you look at the stack content, which is 255, 254, and so on, we should only be using 6 of those locations. And then the other 2, the last 2, should remain untouched. So when you look at the trace here, you can see how we are only using 4 of those locations, and even these 2 are not used. Oh, this one is used too, except it's storing a value of 0, so it doesn't appear to be changed. But then the last 2 columns are not used at all. So it's matching the description of what I thought the program should be using. So that's kind of good. All right, so now that we know the program is working, it is time to trace this manually, just step by step. I can only do this like once or twice because it's very time consuming, but it is also helpful as well. So it's okay to do it, just not all the time. All right, so we'll go ahead and use a new spreadsheet. Okay, new spreadsheet. Because I like to use a spreadsheet to do all the trace because it's already a table. The way I do traces is always one is corresponding to the line number, so we know what it is about. I like to track registers A, B, C, D. There are only 4. And in this particular case, we also want to track locations in RAM. So we want to track location 255, 254, 253, 253, 252, 251, and 250. There are 6 locations in RAM that we should be using. And it's just a matter of reading the code and doing this at the same time. So we want to resize this window so I can have some space left, or at least, yeah, I think I can. There we go. All right, there we go. It's going to be resized a little bit later too. And this is not for this class. Let me get rid of this. That's not it. Where's my code? There we go. All right. We'll save it. Okay. All right, so we'll go ahead and start with, I'm gonna make this a little bit narrower, so this way, it just doesn't, it's just easier to track. So on line 1, D is initialized to 0, as if it is not already initialized because of the reset button. On line 3, A has a value of 2. On line 4, D has a value of 255, because 0 minus 1 is 255. On line 5, we are storing A to location 255, so that means this location ends up with a value of 2. I mistyped this one, sorry. And then on line 6, A has a value of main return. So I think the convention is we use the line number, so this is line 10, or the address of corresponding to line 10. And then on line 7, the stack pointer is decremented to 254, and then on line 8, that is stored at location 254, the return address. So this one now has L10. And then on line 9, we continue execution in the subroutine. Okay, so subroutine is in sum, so that's why the next line to execute is now on line 16. Line 16 copies D to A, so A is now the same as D, which is 254. On line 17, we increment A, so A is now 255. On line 18, it doesn't do anything, so we skip on to line 19. On line 19, we are loading indirect A to A. We are dereferencing A and then store the dereference value into A. So we are looking up what is at location 255. Location 255 has a value of 2, and then we store that 2 back into register A. Is that okay? Because that's kind of important. No questions? Okay. And then on line 20, it is AND AA, which doesn't do anything to any one of these things, but it does set the flags correctly, okay? So because A has a value of 2, the Z flag is going to be cleared. So on line 21, it will make a decision, it will have to determine where to go. And because the Z flag is already is cleared, it is not going to return 0. Instead, it will continue execution onto line 24. Are there any questions at this point? No questions? Okay. So on line 24, we decrement A by 1, so it becomes 1. On line 25, we decrement D, D becomes 253. On line 26, we store the value of A to wherever D is pointing to. So it would be this location that is changed to 1. And let me do this trick here, just so that we don't lose track of the label of each column. And then on line 27, line 27 doesn't do anything, line 28 doesn't do a thing, line 29 is the next one that does something. We decrement D again, so it's 252. On line 30, A has the address of line 33, so we put an L33 here. On line 31, we store that value to whatever D is pointing to. D has a value of 252, so 252 is the one that is changed to L33, which is whatever is in A at this point. And then on line 32, we continue execution in sum. This is the recursive call. Are we still doing okay so far with this trace? Okay. So when we go back to sum, this is where we are at this point. So we're repeating, we're going to execute line 16 again. But this time D has a value of 252, so A ends up with a value of 252. And then on line 17, we increment A, so it's 253. On line 19, we do an indirect access. So we go to location 253 and find out what it is, and then copy that to register A. And 253 has a value of 1. So on line 19, register A has a value of 1. It is changed to 1. On line 20, it doesn't do a single thing except for setting all the flags. On line 21, it doesn't really do anything either because A is not 0. So the Z flag is cleared. It is not going to the label return 0. So we go to line 24, which decrements A to 0. On line 25, we decrement D to 251. And then on line 26, we are going to store. Is there a question, hand? No? Okay, I thought I saw something. So at location 251, which is column J, we're going to store the value 0. Okay, so put a 0 here. And then on line 29, we decrement D, so it's now 250. On line 30, A has the label of return, sum underscore return, which is the address of line 33. So once again, we put L33 here. On line 31, we stored it onto the stack. Whatever D is pointing to, D is now pointing to location 250, which is column K. And that's the location that will store the address corresponding to line 33. And then on line 32, we perform the recursive call again to start from the beginning of the subroutine sum, which it means we continue execution on line 16 again. Do you see how this is kind of repetitive? Okay, but it's the unwinding of things that is kind of difficult to see. So we are not quite there yet, but we'll be there very soon. So we copy D to A again. So A is now 250. And then on line 17, we increment A, which is makes it 251. And then on line 19, we dereference it. We go to location 251, which has a value of 0 at this point, and then store that 0 back into register A. On line 20, we don't do anything that is visible here except for setting flag, the Z flag, because register A at this point has a value of 0, so the Z flag is going to be set. So that means after line 21, we will do the conditional branch to return 0 in this case. So return 0 is down here. So we will continue execution on line 44. Line 44 is subtracting A from A, but A is already 0, so it's not really necessary, but it's good to kind of double check and make sure that we have a 0 in A at this point. Then it's going to fall through. Now this is the important part because we are now starting to unwind the stack. Okay, so we are falling through onto line 49. On line 49, we are going to retrieve the return address. Whatever register D has, which is 250 at this point, we're going to that location and go like, oh, okay, this is L33 or the address of line 33, and we'll put it into register B because we don't want to mess around with register A, which has the return value already at this point. And then on line 50, we are incrementing D, which is our stack pointer, so it will become 251 again. And then on line 51, it is going to branch based on whatever is in register B. So now we continue execution on line 33. Are there any questions about this point? Because this is the first time we unwind the stack. Is that okay? All right? Okay. So the key of unwinding the stack is the stack pointer is increasing again. Okay, we are deallocating stuff from the stack. But the other thing that is important is where are we executing now? We are now executing at quote unquote line 33 because we have finished one invocation, so that we are now continuing with whatever is after the invocation code itself, which is quote unquote line 33, but it doesn't do a single thing. Line 34 doesn't do a single thing. So now we are continuing onto line 35. Line 35 says, okay, let's check what is D pointing to. D is now pointing to location 251, which has a content of 0. Okay, so register B now has a value of 0. And then on line 36, we increment it to 1. On line 37, we increment the stack pointer to 252. And then on line 38, we are adding the two registers. Register B has a value of 1, register A has a value of 0, and we store the sum into register A because that's the first operand. And then on line 40, it doesn't do a single thing except to go to end of sum. Oops, wrong place to click. There we go. So on line 40, it goes to end of sum, which is here. So we continue execution on line 49, which is looking at register D. Register D has a value of 252. We look up 252. It has L33. So we store L33 into register B. Again, we had done this before. And then on line 50, we increment D. We deallocate that byte, which is the return address, on the stack. So the stack pointer is now one more than what it used to be. Line 51 itself doesn't really have any visible effect on these things, but it does determine where we are going based on whatever is in register B, and this is why we also continue to execution on line 33. Is that okay? Any questions? No? Okay. If you're thinking this is awfully boring, it's a good sign. Because that's what it is supposed to be. We are boiling, the mechanism of calling, returning, with parameters and whatnot, all the way down to really, really simple instructions. Okay. On line 33, once again, we are loading whatever D is pointing to into register B. Okay, so D is now pointing to location 253. So we have to look up a little bit now. It has a value of 1. So we store that into register B. On line 34. Whoops, that's line 35, sorry. Okay, let's move on to line 35. But it's the same thing, register B now has a value of 1. Line 36 is just incrementing that 1 Let's incrementing the stack pointer first. Okay, so stack pointer is now 254. On line 37, we increment B itself, it is now 2. And then on line 38, we are adding. So this is the important part. This is the first part. I think this is the first time we actually see something important happen. We're now adding 2, which is the return value of the recursive call. No, I take it back. This is n itself. We're adding n to the value of the recursive call of sum n minus 1, and then storing the sum, which is 3, into register A. And then after line 38, we go to line 40, which is continuing execution at end of sum, the label. And on line 49, we are retrieving whatever is in location 254. Location 254 has L10, which is the address corresponding to line 10. We put it into register B. On line 50, we increment D, which is the stack pointer, to 255. And then on line 51, we do the unconditional branch to whatever B is pointing to. B is pointing to B has the address of line 10, so that means it will be continue execution on line 10. So this is back to main. So on line 10, we don't have a whole lot to do because line 11 is just balancing the stack, so the stack pointer goes back to 0. And on line 12, we are done with the halt instruction. Is that helping? Is it kind of helping you to visualize, what is unwinding? Because we basically keep using more and more of the stack, but as we return, that we are deallocating and consuming what we have stored previously on the stack. Now Fibonacci is a little bit more complex because it will grow, shrink, grow again, because you have 2 calls. But it doesn't change the mechanism. The mechanism of calling, the mechanism of using the return value, that does not change. Is that okay? Now, one thing you might want to do, is to look at the general shape of how we use the stack, okay? And that can be done by zooming out a little bit first. Okay, let me look at where the zoom control is located. I can use the shortcut key probably. No, it doesn't have anything like that. So I can just use a shortcut key because what I want to do is to show you how the stack is, how we are using more of the stack and how it is really kind of shrinking. Now, the way we visualize shrinking is every time we change the stack pointer, it is basically saying this is now the end of the stack, or the end of the stack that is in use. And then when we increase it again, this is the part of the stack that is in use. This is the part of the stack that is in use. So you can see how it is receding. Okay, the part of the stack that is being in use is getting smaller and smaller again as we unwind or as we return from those recursive calls.
So in an actual stack in a computer, or just in general, so when you're deallocating or allocating, it doesn't really matter if the memory location has something in it or not.
Nope, it does not matter. Because if you look at a stack of paper from the side, so you're looking at a stack of paper like this. So imagine this is your stack, okay? Your stack pointer is nothing more than a bookmark. Okay, so originally the bookmark is here to signify the stack is empty. If you use the first page, then you move the bookmark here, then you move the bookmark here, you move the bookmark here. So the bookmark is basically saying whatever page it is right behind is the page that you have used last, that is still in use. But whatever is behind the bookmark is free, it is not used at all. So when you're incrementing the stack pointer, you're moving it from here back to here. Are you changing the content on these pages? No. You're just moving the bookmark to indicate which page is the last page that is in use and what pages are no longer in use.
So I don't know if we talked about it before, but like how exactly does, I guess, changing the input value of the RAM jump to that location? Because it seems kind of just like a hash table. Like you have been written.
Aha, so you're talking about the implementation of the JMP instruction when you use register D as a parameter?
Well, just like specifically in the RAM, like it immediately goes to that spot.
Okay, so that is a good question, but there's a really easy answer to. I like those questions. Okay, so to answer that question, there are several things to look into. Okay, this is something that you should probably do as a part of your studying for this class. Okay, is to figure out how the instructions work in general. Okay, all right. So let me show you how we would approach that. So we go to the assembler, and you can go to the assemble tab, which gives you both the instructions and also the opcode at the same time. So this way it's easier to look at, okay, what is the opcode of a jump and stuff like that. So do you want to look at the jump I instruction or just the jump instruction? One you tell exactly where you want to go to, the other one you say, okay, look at this register, that register will tell you where to go. Jump immediate, okay, JMPI. So you look at the JMPI instruction, okay, we'll just pick one here, here's one. Okay, so row 30 has a JMPI instruction. So what you do is you look at the code that it generates, which is, I think that's the address, this is the opcode. So it has an opcode of 40 in hexadecimal, which is 0100 and then 0000. Okay, now why is that important? Because when you get into the simulator, when you go to LogicSim, which is here, you go to the ROM. If the opcode is 40, where do I find the starting point of the microcode slices corresponding to that instruction? I was just grading your question number 4 today, and most people do not know how to do that. Okay, so looking at this is the content of your ROM. And I want to find out, what is the microcode corresponding to opcode 40 in hexadecimal. Where do I look? 400, very good. Okay, and the reason why it's 400 and not 40 has to do with the instruction register. Okay, so the instruction register is storing the actual opcode itself. But that doesn't directly translate to where the instruction is or where to find the microcode slices. Yes?
I was kind of talking about just like the circuitry of the RAM itself. Like how can when you input like a binary value, it like automatically jumps to a spot, like hardware wise.
But the RAM doesn't jump. It is your PC that is changing, that gives you the effect of your continual execution at a different spot. The program counter. Okay, so that's why all of these things are tied in, because so when you have 40 in your instruction register, that 40 is not going to show up in the microcode pointer as 40. It's going to show up as 400 because we are padding in 4 zeros here in the least significant part. Is that okay? All right. So that means when you go into the ROM, you have to go to location 400 to find out what is the microcode slice corresponding to a JMPI instruction. So it turns out to be a 1F80006. Okay, what does that mean? Well, we'll decode it. Yes?
Like I don't know if I'm like conveying this question properly, but like how does the ROM or RAM it takes input and then it's just like in this spot here. Not specifically like the opcode implementation, but the actual like hardware like voltage, like it's like okay here in ROM.
Okay, so are you talking about the component itself?
Yeah, the component itself.
So you're talking about the component?
Yeah.
Well, whatever the address, okay, assuming the chip is selected, assuming SEL is a 1, this address is actually, okay, kind of imagine that this is a huge, gigantic multiplexer. Not a multiplexer, but it's the A is kind of the select pin of a gigantic demux, actually. Is it a mux or demux? I think it's a demux because it has multiple input and one single output. Okay? So this is the selection, and we have a whole bunch of locations. So the address is just selecting, okay, which one becomes the actual output at the D port.
And does that look on a like transistor level?
Yes.
Okay. That's kind of
Okay. So that's how the A and the D port work together. The A port specifies which location, and then the D port says, okay, that's the content at that location. It's array indexing, basically. Whereas A is the index inside the square brackets, and then D is the value of the array element at that location, at that index. Okay?
Yeah, I was just kind of wondering like hardware level.
Okay.
Yeah. Makes sense.
So you can look at it that way. It's basically there's a big huge controller to find out which cell in the RAM is or ROM is going to use its output to specify the D port. All right. So are there any questions about this particular program or how to use this program to kind of assist you in your homework assignment? No questions? Is it related? I mean, are you kind of making all the connections? Okay. So all the sample programs that we have gone through, the 5712 program that we have gone through last week, this program, and also the program that we went through on Tuesday, they are all crafted in a way that so that they are related to your homework. Okay? So it is up to you to decompose those programs into small parts and then reassemble those smaller parts so that they together it is going to accomplish the Fibonacci program. Is that okay? All right. Are there any other questions related to the Fibonacci program or in general, how do we do summation calls and stuff like that? Mm-hmm.
So I mean, you mentioned earlier that you're going to have to allocate memory and then shrink it and then allocate it again.
Mm-hmm.
So that means.
But that's just moving the bookmark.
Yeah.
Yeah.
So I mean, that means that you call one Fibonacci function just like all the way until, and then you get the return value of that, and then call.
Well, let's take a look at that one. Okay, so instead of using the whiteboard, I'm going to use, well, a spreadsheet it actually is the best way to do it. Okay, I'm going to use a new slide here. Okay, so let's say we are trying to figure out what is the Fibonacci of 3. Okay, so in order to figure out what is the Fibonacci of 3, the first thing we need to do is to figure out what is the Fibonacci of 2. And 2 is already the end of recursion because 2 is one of the special cases where we know the answer is a 1. So then we have to go back to this one, and the next one is to figure out what is the Fibonacci of 1. So that's basically the call structure. When you call Fibonacci 3, it will call Fibonacci of 2, and then we'll call Fibonacci of 1, add up these two values, and return it as the return value of Fibonacci of 3. What about 4? So let's say you want to figure out what is the Fibonacci of 4. It will first have to figure out what is the Fibonacci of 3. And in order to figure out what is the Fibonacci of 3, it has to first figure out what is the Fibonacci of 2. But that is okay. It doesn't do any more recursion because Fibonacci of 2 is 1. We know that for sure. And then it is now free to figure out what is the Fibonacci of 1. Once it has these two, it will go back and say, oh, we know what is the Fibonacci of 3 already. But then it will have to also figure out what is the Fibonacci of 2, which is just 1, and then it can return the result at that point. Is that helping or not? You can also trace the C code. Okay, the C code that I wrote, you can trace that too. You can actually use code blocks if you want to, and trace and figure out what that code, how that code is going to behave. Where is that? Huh?
You saved it.
I saved and closed? Okay, thank you. So we'll go to open recent, sum.c. Okay, well, ignore the sum, but look at the Fibonacci one. So if you want to trace this code, the better way to do this, if you want to analyze how the C code is going to perform, is not to use the return inside the conditional statement, because that's going to make it very hard to see, oh, how do we get this value? How do we get that value? In fact, in here, I will break it up into two statements. so that you can put a breakpoint on one and then have a chance to execute or run the next one. This will make the program very traceable because it doesn't do the return inside the conditional statement.
Oh, so that's what we're doing, right? We're first doing all of fib n minus 1 all the way down, and then it's gonna go back and then do fib n minus 2 all the way down, right?
Yep.
Okay.
But
So can you do fib of 5 real quick? Is that possible? On the
next
on
one.
that Excel spreadsheet?
Yeah, sure. I'm going to do some of the copy and pasting though. So the fib of 5, okay, you have to figure out what is fib of 4 first.
That's not fair.
When fib of 4 is done, then you have to figure out what is fib of 3, right? All right, done. But that's the nature of that call. It's going to go through this. I know there's a lot of redundant. Look at how many times it called fib of 2 and fib of 1. They called it many, many times. But that's what your assembly code is supposed to do as well. Yes.
So in 12 we have first call we do 5, then second call we call 7. That's 2 separate subroutines.
Yes.
And then we have a third separate subroutine which is 12, which is the only purpose is to add those two.
Well, we are
Approximately,
only
yeah.
calling 5 and calling 7. 12 is the caller of 5 and 7.
So inside 12 we will call those
Yeah.
and add. In this program we call it once and then we add just a number to it.
Right.
Yeah.
So it's a simplified version of that.
So which one is closer to Fibonacci will be?
Both. Because each one addresses a different aspect, okay? So when you look at 5, 7, and 12, okay, that program illustrates a particular thing that you need to know. Okay. So if I remember correctly, 12 is implemented like this, right? Return 5 plus 7, right? And then we have sum, which is here. Okay, so let's take a look at these two sample programs because each one, they are both helpful in your homework assignment because they illustrate different things that you need to know. Sum is illustrating how do you make use of your own parameter and pass it along to a recursive call of yourself. That is the main purpose of sum. And then also utilize the return value of the recursive call and then do something with it. Is that okay? That's the purpose of sum. The purpose of 12 is to illustrate, okay, you call 5, cool, now you have the result of 5 in register A, but if you call 7 right away without doing anything, register A is going to be overwritten. That 5 is gone. So you have to save it on the stack. So you have to save the return value of 5 on the stack, then you call 7. So by the time 7 returns, register A would have the return value of 7, but your stack has the return value of 5. So now you have both of those things. You just have to manipulate the stack, pop that thing into register B, add, you're done.
So you have to make sure that, both of them have to have a return address as well, right? Like 12 return. Like 12 would have a return.
Well, are you talking about the return address or the return value?
The return address.
The return address of 12 is determined by whoever is calling 12, like 40.
So you have to have two labels, right? Two like fib
Yes.
n minus 1 and then another fib n minus 2.
It will have 2 points of continued
On one of
execution.
them you save n minus 1, you save the value you save it on the stack, and then on n minus 2 you return it and then add whatever is saved on the stack.
Right, so you have to differentiate. There's the return value, which is stored in register A. There's also the return address, which is stored on the stack somewhere. Okay? So the caller is responsible to set up the return address on the stack. The callee is responsible to set up the return value in register A. Okay, so you make sure you differentiate those two because they're both returning something, but the purpose of those two things are entirely different. And the main confusion has to do with C only has a return statement that does both at the same time. So it specifies the return value, which is the expression after the return keyword, but it also performs the actual return operation to return to the caller at the same time. So that's why we have that big confusion in C and C++, because the return statement is doing two things at the same time. And when we break it down into assembly instructions, then we have to be very clear of this is the return value, this is how we make use of the return address that is already put on the stack by the caller. Yep, go ahead.
So I mean, so the 12 function, calls 7.
Mm-hmm.
And then the 12 function usually has a return label associated with this return label.
Its own return address is stored on the stack. We don't know what that is because it is determined by the caller. We don't know who's calling 12.
Yeah. But 12 has a return label, right?
What do you mean by return label? Like 12_RET?
Yeah.
It has two of those.
Yeah, it has to have two of those because for the first one it processes.
Right, it has.
And then 7 has the return address of 12_return2.
Right.
Yeah.
Yeah, those are two different places to return to.
Yeah.
Yeah. You can also call those, points of continuation or points of, yeah, because they're continuing execution after a subroutine is done. Makes sense now. Very good. Okay. Well, that's the whole point. This is what the homework assignment is supposed to do, is to have you guys to do it. Okay, you run into a problem or run into confusion, you bring it back to class. I try to explain it some more. We go through the traces. Okay, and and as a result, you basically understand how everything works. Okay. And then the sample programs are supposed to be helpful too, because each one illustrates a different aspect that you have to do in your program. Yep.
Well, I mean, I guess I always thought when a computer was processing stuff, it was like it all just happened at the same time. But it seems like you call a different function, it has to go through each one on the stack separately.
Correct.
But if there's multiple processes, is that completely different?
No, that's a whole different thing. Yeah. For the most part, when we write programs, any program in C and C++ are inherently single-threaded. Okay, I'm not talking about the.
This is threading.
This has nothing to do with threading, but when you write a C program, you cannot express parallelism at all. You cannot say these two things can happen at the same time. You spin this one to one single processor, put one core on this part, put a core on the other part. So until you actually use pthread in operating systems and stuff like that, C itself has no feature, no language feature to express parallel threads. So when you write programs, it's a single thread. So when you have calls upon calls and you have the return value of this call used as a parameter in another call, they're all happening sequentially. They're not happening at the same time. So next time, I know we are running out of time today, so next time what we'll do is to write something like this, okay? So we want to implement the max subroutine again, but instead of just max 5, 7 like this, we're gonna do it like this. So what do you do? What do you do when you have a call like this? You call 5 first, right? Push it on the stack as a parameter of max, but you cannot call max yet. You call 7 next. Push it on the stack. Then you call max.
Then once you max, you give some register A to 5, you give to register B a result of 7, and then you add it.
No.
But that's how you did it. You saved it in the stack, and you handed it over to some register.
But it's the opposite order. You have to call 5 first. Whatever 5 is returning in register A, you push it on the stack.
Right.
Then you call 7. Whatever 7 is returning in register A, you push it on the stack. Then you call max, because now max has both parameters on the stack. When max returns, then I did not specify what you do with the return value of max, so that's unknown. But if it is if this is a part of an assignment statement, this is the right hand side, then you have to store it to somewhere.
Yeah.
Okay, but this is just giving you an idea of the sequencing of things. You can have calls. this is actually not much different compared to this. If you think about it, this thing here is actually very similar to this one here. All you have to do is to, instead of seeing this as max, make it plus, or make it sum, or something like that. Okay, so now you understand the concept of, oh, you just have a specific order of doing things, figure out what is needed, and then do whatever is depending on that something that you have just computed.
Just a quick clarification question. We describe in the max and the plus, we actually describe saying the value of the subroutine 5 and then do 7. But I was the impression that we're supposed to push the last parameters of the stack first. So would it be?
Yes. So it would be
seven.
very good. Okay, that's a good point. You have to call 7 first, push that on the stack, and then you call 5 and then push that on the stack. Very good. Yeah, because you have to push parameters in the reverse order. Yeah. Good point. Good job. All right. So we're running out of time in the lecture. I will go to the lab. So if you have a program that's partially working but you're not explaining why it is partial, then we'll go ahead and take a look.
It makes sense.
No, but I was thinking about Dixon's thing. I just clicked. I was like, oh my god.